Hello everybody, my name is Vince Bickers. I work for GraphAware. I've been with GraphAware for about 5 years now. I'm kind of a funny position here following Alessandro because some of the things that I want to talk about he's already touched on in his talk. We didn't actually communicate very much beforehand about what we were going to be talking about, but obviously Alessandro's talk was very doctorish, very PhD level. For those of you who find it difficult perhaps to follow all of it, this one is going to be a little bit more practical. In fact, we're going to pick up on some of the issues that Alessandro raised during the first talk, particularly about the fact that we have masses of data now and how we're going to process that, and particularly in terms of the graph as well. I want to look at that. So I'll get going without further ado. And these three issues. I mean, there are many issues with big data, obviously. But because we have so much of it now, everyone's realized actually there's a lot of information to be had, as Alessandro was saying. There's a lot of information to be had out of big data that people would like to have, companies would like to have. But there are three main problems. I mean, there are many problems, but three main problems are volume. We now have so much of this stuff coming through. You look at Twitter, how much stuff you can get from Twitter. You look at the Facebook graph, how much data is actually in that graph. And you can download some of that stuff. And there's also coming more and more of it. It's coming faster and faster and faster. So we have a problem with actually getting data into our systems to analyze, to use, to make decisions with, just in terms of actually how fast we can process it, how fast we can ingest that information. And the other big issue is how much different kinds of data there is. Before, we perhaps were looking at some information from the accounting system locally in our own company, and we had a bit of this, and we had some information from the customer sales team about this, and we could handle that sort of stuff with our relational databases. But now we can't, because we have other stuff coming in. We have information about people's social networks coming in, who they're talking to, who they're tweeting. All this information is important now for customers, for companies, people who want to make decisions about how they should best talk to their customers, how they should best deal with their customers, how they should make decisions internally, as Michael was talking about earlier on. We now have access to all our email content. What can we learn from that? How can we improve? So we have this enormous amount of data, and we have it coming very fast at us, and we also have a lot of different types of data. And these three things directly impact our capabilities to, first of all, discover stuff that's important. We have lots of data, but what we need to do is to turn it into information. Secondly, we don't know how to contextualize it. It's very difficult. I might have got 5,000 emails, and I can find out that somebody has mentioned the word Java in this email lots of times, but I need to contextualize that. Michael said, how do I contextualize this information so I know whether this is someone who is leaking information out of my company or whether it's normal in this situation for somebody communicating about this sort of stuff. So it's hard to contextualize. And finally, it's hard to analyze because the more data we have, the more we try and process this data, the slower our analysis cycles can become. And we don't want to be responding to events that are happening now until, if we have to wait 2 weeks to respond, sometimes we may have missed the boat. So these are the three things that I think we are becoming increasingly impacted in terms of companies' abilities to respond rapidly to these increases of volume, velocity, and variety in big data. And an important answer, is we've got to stop thinking about just stuffing everything into relational databases. We have abused our databases, something rotten, for the last 5-10 years. Even now, I see, even with NoSQL databases, I see people using Elasticsearch, for example, as if it was a database. They put everything into it, and then they try and figure out why they can't get the results they want from it. And the problem we have, we've got to start thinking differently about how we manage this data. It's no longer sensible to put all of it in one place. We have to put the data where it's needed for the purposes we want for it. And this is what we call polyglot persistence. as a term I think was invented by Martin Fowler some time ago. But the other thing is not just polyglot persistence, which is where the data is stored, but also polyglot computation, where we are doing our analysis of that data, where we're doing the number crunching on that data, or we're looking through the graph, or whatever it might be. We have to move those computational processes to where that data is, but we've already distributed the data. So because we've said we want to have the data in the appropriate data sources for the kinds of problem. So what this means is we're ending up with a distributed data platform, effectively, for handling big data. One thing I like to think about often is that if you take the example where we're trying to search through our emails, for example, we've got 100,000 emails over 10 years, and we're interested in finding out what's been going on and so on and so forth. The first thing we need to do is search. And that's like text search. And we don't do text search in graphs, because if you did a text search in a graph, you'd be spending forever. Graphs aren't good at that. But other tools are very good at that. Elasticsearch, for example. So that's where you'll be putting your large content of information. You'll be putting that into something like Elasticsearch. So it could be properly indexed, so you could find out all the terms, term frequencies, and so on and so forth. But that on its own only steps the first thing. Now you can discover stuff because you've got a fast search engine. But how can you contextualize it? How can you know that what's relevant or not relevant, and the context in which this information is being provided from you for your search? So this is where the graph comes in. This is where the graph comes in. Neo4j, this is where you can have check your relationships between the things. But what you're not doing in Neo4j is you're not storing all of that textual information. What you want to do is to keep that minimal in Neo4j. So you're basically storing just the nodes with sufficient information on them and on the relationships to tell you that you need perhaps to go back to Elasticsearch and pull out some more information at this point. In other words, you're looking at some cooperating processes and cooperating databases here in order to enrich the information that's coming out. So that's kind of how you can contextualize some information through search. The final step is analysis. When you're doing large-scale analysis like K-neighbor analysis or something like that, or some kind of community detection, sometimes your data is just too big. And also you're using your database for operational reasons as well. And you don't want to tie up computation processes on an operational database, a graph database. So you can move that computation out. And if you imagine that you had a stream of data coming in, maybe on Kafka or something like that, and you have all this information about your emails and other stuff coming through, the way that you would think about probably building this and meeting this challenge of how do I get sufficient information fast enough to make these decisions, is you can imagine that you've got these different data sources pulling out just the bits of the data that they need. They're just listening to that data stream and pulling out the bits that they want that suits what they have to do, which is in the case of Elasticsearch is to obviously index all that data. It's in the case of the database, it's going to the graph database, it's going to be just extract the nodes and relationships that are pertinent to the types of things you need for your business. And then finally, so your analysis platform, Hadoop or Apache Spark or whatever it might be, it's going to be doing the number crunching. And it might be pulling just some information from there, from the mainstream, but it also might be pulling stuff that the graph was built for it as well. So there's all sorts of things, ways that these three components in this kind of like search, contextualize, and analysis approach can communicate with one another and enrich the information back to each other as well. The point about this really is that if you try to do everything in a single database, whether it's a NoSQL database or if it's a graph database on its own or if it's an old relational database, even a very fast relational database, you will come unstuck because you just cannot do all the different kinds of things you need to do in order to bring this information out. So that's polyglot persistence and computation. And when we talk about context, I've already talked about contextualization being a graph problem. It is a graph problem because a graph allows you to discover all these connections between the items of interest that you have found from search, for example, or from another process that is going on in your business. The graph allows us to tell us who's talking to who. Maybe I've got lots of phone records and I need to find out who's talking to who. Or I may be tracking some individuals who are criminals and I've now got their phone numbers and I've got some information about their phone numbers. And so I can find out who's talking to who and maybe take some action about tracking them down. What are the travel patterns of certain criminals? You know, I don't need to know all the data. I don't need to know the date of birth of the criminals that I'm tracking. I don't need to store that information in the graph, but I do need to know what flight they caught, when they caught that flight, and who perhaps else was on that flight with them. So these are the sorts of things I'm talking about. You minimize your data. What happens if this airport is closed because of a hurricane alert? I mean, we've had 3 hurricanes now in the West Indies and in the Caribbean. And what a graph is ideal for being able to tell you, because it's a network of connections, what happens if this airport shuts down and all these flights have to be diverted? And this is the sort of thing people are using graphs for as well. What product should I be recommending to my online customers? So this is all graph stuff. It allows you to contextualize your information that you have and then make decisions based on that. So I think we've already talked a little bit about Neo4j, so I'm going to quickly skip over these things. But basically, we've seen a graph database consists of nodes, which represent things that can have labels, types attached to them. And then there are relationships or edges between those things, which carry semantic meaning. Somebody knows somebody, or somebody follows somebody on Twitter. And they can have a type, as we just said, but they can also have a direction. I love my wife, she loves me. So we have a relationship that's sort of bidirectional in that way. So we can relate nodes by type and direction, and finally we can stick properties on them, name-value pairs that can go on these things. So particularly important for graphs is weighting of edges. So I might have, we're talking about, say, a social graph where we have some concept of closeness between people. We can measure that with a weight on that edge, and that can help drive the decision-making processes and the ML stuff, that machine learning stuff that Alessandro was talking about. Those algorithms about clustering, about who knows who, and so on and so forth. So that's Neo4j very briefly, and I just want to show you a pretty picture there. Really, it's really easy to visualize the graph. That's the point. As I think Michael mentioned this earlier on, you've got 5,000 emails. It's really hard to see what's going on. But if you pull the pertinent information out into a graph, it's very easy to follow those things and see what's going on. Now, I want to talk a bit about something called mechanical sympathy. The reason why Neo4j is so good at what it does is because it is built around it's architected around following the practices, the way that the operating system and the CPU, modern CPUs work. I don't know if you've ever noticed this, but if you, how many people program here? A show of hands? A fair few. Okay, so if you've ever taken suppose you've got a large array of numbers, I don't know, 1 million numbers, integers, right? But they're all within, you have 1 million of them, but they're all within a particular range of, say, 1 to 500. So you've got a list of numbers, many of which are duplicates. If you order those numbers sequentially from the lowest to the highest, and you run a sorting algorithm on them, they're already sorted, of course, but you run a sorting algorithm on them, it'll run much faster than if they are unordered. And you think, so why would that be? I mean, yes, okay, maybe not, but a lot faster. And the reason is because CPUs are based on sequential processes. They read their pipelines in fast, and they have branch prediction going on. So they are not expecting, they hope, rather, that they don't have to make a change. So because your numbers are already ordered, like this, they never have to switch and say, oh, I've got to swap this number, and so on. So little things like that make a big difference. And when you look at disk speeds, for example, disks, SSDs, solid-state devices, they are very fast, and they are obviously optimized for random reads, and they're super fast. Mine is amazing, blindingly fast on this machine. But actually, some hard disks, some traditional HDD drives, are faster in sequential I/O than modern solid-state devices are, because the operating system and the CPU and everything is optimized for getting data off that disk as fast as possible and streaming it through. And Neo4j is built to support that sort of concept, or from the ground up, basically. It's designed to operate in harmony with the way that the operating system works and the CPU works. And the way it does it is it basically stores everything on disk as if it was a set of pointers that could be followed one after another. So when you start in a graph query and you have a node and you're trying to find all the relationships from that node, it doesn't have to go anywhere else and look. They're already there, pointers. It just jumps from one to one to one to one to one. And because they are all laid out sequentially, they're all in the same CPU cache line as well. So this is what makes Neo4j particularly fast. And Neo4j call this approach the graph native approach. And you'll hear them talk a lot about the benefits of the native graph, all the way down to the disk, all the way up into the graph model itself in memory. But in fact, that's just half the story. Because you can have the best engine in the world, but unless you are, going to put Formula One car, if you put me in a Formula One car, I'm not going to be doing very well. So what you put into your graph is just as important as how good the engine is as well. So I want to look at when the challenges, we talked about the challenges about big data earlier on. What do we do to mitigate against the issues that we had there, the volume and so on and so forth? And we've already talked about a few of those things. The first is, and Alessandro stole this line from me without even knowing I put it there. You must use the right tool for the right job. We've already talked about that. If you're doing search, don't do it in the graph. If you're doing analysis of connections, do it in the graph. Decouple your architecture. We talked about having these systems loosely coupled so that they can pull the data they want without affecting the other systems around them. That means that you can make changes to one system and it won't affect everything else. These are all sensible things to do. The other thing that's really important for the graph is to localize and minimize the data that you're collecting. So by localization, I mean basically you're only going to take the bits that go in the graph into the graph, just for that. You're not going to put anything else in there. But to minimize it, I mean don't take any more than you absolutely need to do your queries. And the reason for that is quite simple. It's because of mechanical sympathy. When you have a lot of properties on a node, for example, that you need to search through, half of those properties are never going to be anything that you need to search through, but you just collected them just because they were there. That will slow down the engine as it iterates through this list of pointers to find the property that you want. The same is true of relationships. If I have a node which has got many, many relationships that I'm not interested in, I shouldn't be capturing them. Just because they're there, I shouldn't capture them unless I actually need them, because the same process of iterating around those relationships means that your traversals through the graph will slow down, and you're after finding this information as fast as possible. So localize and minimize the data you're collecting. And as a corollary to that, don't hold on to the data for longer than you need it. You might be collecting information about people's email habits, for example, email traffic within your company, and you've got 15 years of it, perhaps. But actually, you're not interested in what happened 15 years ago. And while you're holding all of that data, the same problem arises. You've now got all these extra nodes and relationships to traverse. You need to make sure that you know how much data you need to solve the problems you're trying to solve. So all this comes down to being smart about data ingestion, really. Make sure to get the stuff in only that you need and don't hold on to it longer than you need it for. And that means, of course, that you can keep building your graph on a sort of moving sort of window like this as the relevant data stays with you at the time, and the irrelevant or less relevant data can drop off the end, maybe be archived or something like that. In terms of hardware, if you're running on Linux and things like that, you need to ensure that your I/O subsystem is fast enough for graphs, particularly because Neo4j is so good at asking the operating system for data. It's not got any internal caching going on, very, very little internal caching on. It's all memory map files. So you need to have your IOPS up, your I/O per second. That's got to be very good. So that's something just from a technical point of view to make sure when you're installing Neo4j on the machines. And finally, write efficient queries. These are the sort of things where, without thinking about it, you can write a query that goes through what we might call a supernode, a node which has got lots and lots of relationships attached to it. And all you need to do is actually find something else on the other side of that. But there's different ways that you can approach that problem. You can avoid going through to get the supernode to look like this, you can go through the two ends of the thing and come and join to the supernode in the middle that way without having to do lots of traversals around all these relationships in order to come out the other end. Those sorts of things. I don't want to go into too much detail about it all now because there's a lot of things to do with writing efficient Cypher and so on. And you'll find a lot of this on the internet as well. So Stack Overflow and places like that, our websites and so on, our blogs and the GraphAware website. So that's the sort of things you need to do in order to give yourself the best chance of getting the data in quickly and efficiently with big data in Neo4j. Then we actually have to look at the actual problem of data ingestion itself. We now know we've got our principles in place. We know what we're going to collect. We know we've minimized our data sets to support the queries we want to run. But there are some operational problems now we need to overcome. And Alessandro alluded to this earlier on when he talked about all the different numbers of the kinds of data that now need to be amalgamated together to support this kind of big data machine learning paradigm. First of all, we have to integrate all these different multiple data sources together. And most of the information that's in them, we're not interested in for our particular purpose, but we might be interested in just 2 or 3 items of information from every record in this database. We're interested in tweets that are this, that, or other kind of, have some characteristic or other. And so we're pulling all these different data sources together. And in the past, of course, we didn't used to do all this. We used to just pick up some data from a CSV file and load it in, and that was it, But now we have a lot more to load. The other thing we have to do is to think about filtering that data. Much of it might be irrelevant to what we're interested in. We don't want to, and we saw before, we don't want to load it all into the graph or into Elasticsearch or into whatever our data storage is. We do not want to load more data than we need. So we need to filter data. We need to be able to convert data. And we need also to handle non-standard forms. So, everyone knows you can load a CSV file, but what happens if you've got a GPX file of coordinates or something like that, some geospatial coordinates, and how do we load that? How easy is it? And we end up writing code ourselves, and it doesn't work properly, and then we go again the next time we have to do it, and so on and so forth. We have update strategies we've got to handle. How do we deduplicate data? Sometimes we want to eliminate any identical things that come through. Sometimes we want to merge because we've got a set of properties in the first version and a different set of properties in the second version, updates effectively, and want to merge them together. Yet other times we want to keep a history of changes over time, so we want to version our data. So we have a particular information about a customer coming through, and we want to keep that versioned over time. So we have different update strategies we've got to think about. And then we have to think about bulk load. How do we get the data in very fast, and then how do we then incrementally update it later on? Ease of use and configuration of any tooling that we have. How easy is that to use? Because all these things will be barriers to you when you start to try and ingest data into any kind of big data platform where you want to use a graph. And then finally, performance. It's no good waiting for 5 years for your data to load when you have a problem that needs to be solved next week. So all these things, I think, are sort of the major operational problems to overcome when you're looking at, particularly for the graph, to ingest data into Neo4j. And we've had a few options up to date. We've got Neo4j's own load CSV, which is, as it says, load CSV files, and we'll have a look at that in a second. There's also the batch importer from Neo4j, which does things very differently and has a different purpose. And a fairly recent addition from Neo4j is the ability to connect to a JDBC data source and suck data into the graph from that JDBC data source. And then we've got Databridge, which I'm going to talk about in a bit. I just want to look through these different options first. So I don't know if any of you are familiar with loading data through into Neo4j, but load CSV has been the oldest and most traditional way of doing this. And you have to run Cypher, which is the Neo4j query language. You have your CSV files, and you load them through a Cypher query, and you say how you want to match the different columns to different nodes and properties and relationships in the graph. The real problem with it, it's very flexible because you can do anything you like because you're writing Cypher, basically. which means you've got complete control over the graph database. The difficulty is that, A, you can only do it CSV files, so you can't load JSON, for example, this way. You can't really load large data sets because of the way it works. It will slow down and slow down and slow down over time because it basically has to run transactions and it has to keep checking for duplicates, and it takes longer and longer and longer and longer. So there's a limit to the amount of data you can load with load CSV. You do need to learn Cypher as well. So if you're not the kind of person if it's your job to just get data into databases, okay, you might have learned SQL, but are you really going to want to learn Cypher as well? Maybe you will. I don't know. It's a nice language. Relatively slow. That's the other thing. It's not, the database is online. Everything is going through a transaction handler all the time. It's being checked for record locks and so on and so forth. So it's slow, relatively. And the other thing about it is it's very difficult to manage complex imports because you've got one CSV file here, and then you load another one, but you've got no context for the one that's just been loaded. If something needs to happen because of this piece of data in here, you've got no context, perhaps, left. So it's difficult to manage complex imports like that, and you certainly can't load different kinds of data stores using load CSV. To counteract this problem of performance, really, the speed problem, Neo4j have got a batch importer as well. And this works with the database offline. So you don't have any users connected to it. It's quiescent. It's really fast. And it can handle huge data sets. So it's got a lot of things going for it. The only problem I find with it, and I think lots of people find with it, is the reason it is so fast is because we talked about earlier on mechanical sympathy. Neo4j know perfectly well that if they could write all their node records out in one long sweep to the disk like this, and all their relationship records on one long sweep to the disk like this, they get massive throughput. And that's exactly what the Neo4j batch importer does. But it does require that whatever data you're trying to process beforehand gets pre-processed into CSV files containing all the nodes and CSV files containing the relationships. And if you're talking about hundreds of millions of rows of data, that's a lot of pre-processing to do. So there are some sort of downsides to this, which means that it's inflexible in that regard as well. Once you've got your data in that format, you can't do anything with it while it's being loaded. You can't intercept it through some kind of, okay, this particular piece of data I just want to chuck out because of some information that's elsewhere in the data set. You can't do that. And it has no memory. It can't remember what's happened before, and so it just keeps blindly churning through the data that you've pre-prepared. So there's a lot of processing you need to do if you're going to use the batch importer. So it's great if you've just got a single data set you just want to load, but we're talking now about trying to join data sets together from different resources in order to build a composite view in the graph that we can use for our machine learning algorithms. The latest one is the JDBC. It uses the batch importer, so it is very simple. It connects to a JDBC database. It reads the JDBC schema, and it says, okay, right, I'm going to pull this into a table, this table into some nodes, and these joins over here can become a relationship on the, and so on and so forth. So the good thing about it is it generates configurable mapping files, so you can actually tweak them before you then run. It's a two-stage process. Generate the mapping files, then run the actual batch importer at the end, which is what it uses. So it generates the CSV files itself and the relationship files. Again, you can only use it for JDBC. It's like I've got CSV here, I've got batch over here, and I've got JDBC over here. But unfortunately, I've got nothing I can just pull them all together with. And again, it has no memory. So these are real serious problems. When you're trying to get data into Neo4j, and the data and the graph database is a critical part of your infrastructure and a critical part of your ML stuff, these are issues that you need to solve. Hence, we have Databridge, the unified data ingestion platform for graphs. Hooray! Come on. Okay. Okay. So I've talked about the issues that there are with all of these different kinds of ingestion problems. And at GraphAware, we've been building, solving these kinds of problems time and time again over the last 5 years or more, and which has basically meant that we've built this platform. And we've taken a really simple approach. The simple approach is, why do people have to do all this work? We let the platform do the work. After all, we know what resources we want, and we understand what we want it to look like in the graph. So why can't we just describe those different things, build a bunch of adapters, and then have a platform which allows you to ingest this data from all these different things, go through these adapters, and just generate the graph for you? It's a good idea. And this is pretty much what it does, exactly this. So we have many different data sources. I've just shown 4 here. I've got some grey black circles on those adapters. They weren't there earlier. They've come back again. Ignore them. We have some adapters whose job it is to basically take the different forms of data that we're loading and transform them into a common format for the engine to process, from which a graph or graphs will be produced. It's a really simple concept, and it pulls together all of the best parts of CSV and the JDBC and so on and so forth. So we have JDBC connectors, we have Kafka, we have CSV, we have Excel, we have some bespoke adapters for particular other non-tabular formats and so on and so forth. And at the end of it, you get a graph. So these are, I think, the compelling features for Databridge. First of all, it's really easy to use and configure. We're actually going to look at it in a minute and put it through its paces. It's fast, it's scalable. We have strategies for handling duplicates that I talked about before. How do I want to choose whether this should be a unique item or version it or whatever. We have adapters for all these different kinds of data sources. We do automatic conversion from JDBC to the graph as well. Again, we do, just like, in fact, the JDBC connector does for Neo4j. We also have filters and data converters. We can do full and incremental imports. So we can do a full import and then just a little bit later on to update those things so we don't have to do everything. We can do offline and we can do online. And it's extensible. So if you have a particular data source for which there isn't an adapter, there's an API. And you can just extend it and put that adapter in and say, this is my adapter, I want to use this for this data, bang, and it will run, and it will work. We've done it so many times with our own adapters that we know it works. So I'm going to show you how simple it is to define a resource and a schema mapping for data. How little you have to do in order to get data into the graph using the Databridge platform. Text file adapters, obviously they process common file formats. And you can just see the resource definition is fairly obvious and very simple. That's all you have to do is just specify the resource. This is what I want to load. We do wildcard selectors. If it's local on your local file system, you can use wildcards. You can get your data over different transports. So you can use FTP or HTTP. For example, we're pulling some JSON over here, over FTP. And you could load Microsoft Excel spreadsheets as well. So you don't have to export them out to CSV. There's an Excel adapter for that. I think that's a file system storage type. For JDBC, we are compliant. We will work with any compliant JDBC database, any JDBC compliant database. You just basically, we won't give you the drivers because some of them are not free. Install the appropriate driver. You just drop it into the lib directory. Configure, like I've shown you here. In the first one here, we have a JDBC connection string and a query, which we're running a direct SQL query against, so it's going to pull that data out. But we can also do the second type of thing where we actually pull much more complex queries that we want to run, and we put them in files, and it will execute those SQL files as queries as well. And then most recent, but also most interesting, we have Kafka as well. So now we can read from Kafka. From every adapter will read, or every instance of an adapter will read from a single topic and partition. And it will run for as long as Kafka is running. So we've changed the paradigm somewhat now. So before we said, okay, we just want to load this data and that's it. But now with Kafka, we can keep running. And more data comes along and we'll ingest it. And we'll keep updating the graph and updating the graph and updating the graph. We also have the ability to time out, however. So if you don't want to wait, if you don't want to keep this thing running when you know there's no more data coming, you can set a timeout on it, maybe 20 minutes, half an hour or something like that, and it will terminate after it's received no more messages after that time. We can also seek to different positions in the Kafka and the topic partition, so we can go to different points where we can start reading from. By default, it will read from the last committed sync point. But we can also seek to anywhere else we want. Seek 0, you can replay the entire stream. So if you've missed some messages, seek backwards, and you can replay them back into your graph again. Okay. Schema mapping. So we've seen resources. That's just a single, that's called a resource definition. Very simple. And schema mapping, go back. All it has to do is define the resource, which we've just seen. It needs to describe how that resource should be mapped from nodes and how it should be mapped into edges. And I'll show you a very simple example here. So this is the Hawkeye schema. We're going to have a look at Hawkeye in a minute. You can see the resource definition at the top. It's basically using a file that contains that information that we saw with the resource descriptor in it. And we have creating nodes. And we're creating a node called phone, but actually we're subclassing it. We have a node from and a node to, a phone from and a to phone, but they're both phones. So we say phone from and phone to. And our record information just basically has 2 phone numbers in it and a timestamp, I think, when the phone, it's very simple. And then we don't have to do this, but we also have the edges that we're going to create between these 2 phones. It's really simple to understand, very easy to see what's going on. Normally with Neo4j, and you don't need to reciprocate your relationship. You don't need to have a send and a receive between the 2 things. But I wanted to show you that this works and how fast it is even to creating redundant relationships in the graph. So that's really how you do this. And you can then add any more of these schemas that you want, these schema mappings. You can have multiple schema mappings running in one import task. And you can have lots of different data sources attached to each of those different schema imports. So you can be pulling one in from some CSV files, another in for some JDBC stuff, another in from some JSON over the internet or something, and so on. And then you can have your Kafka as well if you want to do that. So you've basically now got the ability, as Alessandro was talking about earlier on, is to pull data in from all these different resources and combine it into a single view in the graph. First time ever this has been possible. First time ever. So we're going to run a demo. We're going to run the Hawkeye demo. I have 10 million phone calls. They have been anonymized. And we're going to import them into Neo4j in less than 1 minute. And we're going to find out who's been talking to who. OK, so this is the Hawkeye demo. So what this is going to do, I have 500 million rows of data in this data set, but I'm actually only going to load 10 million. Otherwise, it would be... OK, so we're now loading data. We're loading data. We're loading these records into Neo4j now. And I want to show you just how fast that's going through. So I don't know if you can read that, but we are now already we're on 3.6 million rows of data. And we're actually importing objects into the graph at more than 1 million objects per second into the graph. So we have got some very good performance, which means that when you're trying to do your big data stuff and you have to get this data in quickly, this platform will help. Because we've got some, there we go, what do we got there? 36 seconds, that's faster than it's ever done it before. And that's 10 million records. We could have done 100 million, couldn't we? I just had to talk for longer. Okay, so let's see what we've got in our graph. We have phones here, and we have 2 relationships. I mean, one of these is redundant, because obviously the person sending is the opposite of the person receiving. But let's have a look and see what we've got. There we go. These are our phone calls. 10 million phone calls, some of which were duplicates, obviously with same phones, talking to different phones and so on, loaded in 36 seconds in the graph. Now, obviously, we could have added other things in as well. So now you've got your phones in there. Perhaps you also now start wanting to put other things in from different data sources about these individuals with these phones. Maybe where they've been traveling, as we were talking about before, and so on. So you start putting some information about that in. Maybe the cell tower stuff, that you can track where their phone's been. And suddenly you're building some really interesting information about people and what they're doing and where they're going. And if you're trying to track criminals, you have a lot of information suddenly at your fingertips, and you can get it in fast. So that's really where I want to finish. I wanted to talk about how you can get big data into Neo4j. This proves that you can. And also some of the things that you have to do to make sure that you get the data in without getting more than you need, because it will slow it down during your ingestion process, during your query process, and so on and so forth. So I hope that's been interesting for you. Any questions?
Yep. About schema mapping, so it can be only like mapping as a document, or it can be some kind of program, because sometimes you need cycles, sometimes you need a little bit more than just JSON.
Okay, so I've only shown you a very small amount of what you can do in a schema mapping file. We haven't talked about the fact you can put conditional attributes on there. You can say, I want to conditionally create this node. I want to conditionally create this attribute or this property. I want to create a label only when, blah, blah, blah. There's a lot of stuff. We haven't found yet a case. I'm sure there are cases, but in the cases we've been dealing with so far, what we've tended to do is respond to new requirements as they've come up. So, okay, we need to do this, we need to do that. So we have data conversion automatically in there. You can just specify a converter. You can write your own converters in Groovy, drop them in, and it will pick them up and use them. You just declare them in the JSON file. So it's quite a powerful schema mapping concept. I'm sure there will be times when you may need to do something programmatically, in which case you can use an API and you can build a mapping file with the pieces of data in that you wanted. Whether or not it would give you any advantage over what's available now, I don't know. But I mean, it'd be interesting to see if you've got a use case that we can't do. Alexei, you're on. Yeah, any more questions? Yeah.
When it was released?
Okay, so this, Michael.
I don't know. It's never really been properly released. I'm just joking. Well, you've been working on it for
3 years, about 3 years. So this has been a stealth project, basically, for a long time. It's been a stealth project, and it's been tested with clients of ours. And they have received copies of this, and we've made adjustments and improvements as they've found issues and so on and so forth. So it's been on the basis of working with our customers that Databridge is in the form that it's in now. And we believe that it's probably ready for the big time. One of the things we want to do, and we're in the process of doing, is adding a user interface onto it so that you can drag and drop and create these schema files without having to type text. You know, if you're a developer and you like the keyboard, that's fantastic. But not everybody does. People want to be able to have a sort of UI on those things.
Well, exactly. I mean, our use case is pretty much completely in the hands of BI users rather than
exactly
tech.
right.
It's therefore a UI is absolutely essential for it to adopt it.
Exactly right. Yeah, we know that. You know, even with the minimum amount of work you have to do now compared to what you had to do before, it's still going to be too much for some people. So that's the UI is the next thing. We haven't decided yet on the licensing model for this. So come and talk to us if you're interested, basically. That's all I could say about that right now, I think, without giving away any more secrets. Any other questions?
Such question: which amount of data is reasonable to save in one single instance of Neo4j, and is there a possibility to have like a cluster to handle a big amount of data if, let's say, we will just use a big social network like Facebook?
Yeah.
Yes. So there's in terms of the amount of data you can hold in Neo4j nodes and relationships, it's virtually limitless now. There was a limit before, but the Enterprise Edition pushes that limit to beyond what anyone is ever going to be able to load or store. The issue is going to be how fast you can access that data, how quickly you can run your queries on it, and so on and so forth. And there's no reason at all why, if you have billions of rows, billions of nodes in your graph and billions of relationships, you cannot run that graph queries on that quickly. But you have to know what you're doing. We talked about some of the things beforehand. If you start putting lots of unnecessary properties in there, lots of unnecessary relationships in that graph, then you're going to slow down because it's got a lot of data to crunch through. So you have to be very lean and mean about what you put in the graph when you're talking about this kind of scale of data. But there is no practical limit. Now, there are other things that people do. For example, it's really difficult to partition a graph. Some people think they can do it. But the real problem with partitioning a graph is that because it has to be connected, the minute you partition it, you separate. So you've got part of the graph running in one machine and part of the graph running in another machine. And sure, if you've got some hugely fast connection, network connection between the two, maybe that could work. But most people don't have that kind of hardware at their disposal. So one option people have is they run all of the graph across a cluster. But they run hot parts, different hot parts of the graph. So if, for example, I know that I want to go and get particular geographical information for geographical zones A through to M, for example, I'll be running that on this cluster, and the query engine will know to direct to this particular node for that data because it's warm and in the cache, and they don't have to fetch it all off disk. Even though fetching off disk is fast, if it's in memory, it's even faster. So that's the option people take to partition the graph. It's called cache sharding, really, but it's kind of like you keep different portions of the graph hot, and you go to the bits you need for those parts, rather than trying to go to the cold graph. But there is no theoretical limit to what you can store in Neo4j now. Certainly not anything practical. The more memory you have and the faster disks you have, the better it will be. Use SSD all the time, obviously, and use lots and lots of memory, because Neo4j loves memory. It pulls it off the disk super fast, so it fills memory fast as well.
Do you have any numbers related to the live streaming in performance?
In terms of what, sorry? Oh, for sure. Yeah, we didn't show about that, did you? So yeah. So sure. Yeah. So we talked about having the offline and online abilities. What I just showed you there was the graph was offline. So what we were doing was we were writing directly to those disk files, as I mentioned earlier. We were writing straight onto the disk, and that was very, very fast. When the database is online, we also support online, obviously. And when the database is online, you're going to be quite a lot slower because you're going to be running Cypher in order to get the data into the graph. So my recommendation would be that you bulk load everything first offline, and then you take your smaller incremental updates online in the live database while you're still operating it. Then you're not going to have these problems of like performance. But really, if you're trying to load billions of rows of data using the streaming endpoint, I wouldn't recommend it. It's not designed for that. You're looking probably 10 to 50 times slower. Maybe more, actually. We've got 1 million objects per second then. I think probably we can do probably 50,000. So we're quite a lot slower on the streaming endpoint. So don't use it for bulk load.
Thank you.
Okay, thank you very much.